Okay, so today we are going to uh, finish the geometry part of ray tracing, hopefully, and we will start the shading part of ray tracing on Thursday. And we'll probably announce your first assignment this Friday, and you will have 3 weeks to work on the assignment. And the entire ray tracing algorithm, we'll finish most of it this week. I mean, you may complain first that, okay, we haven't finished ray tracing, but you're given an assignment on Friday. But actually, the algorithm is the first parts of the algorithm. You can start coding right away. And you're going to do some coding today as well. I'm going to do the coding in such a way that my main concern will not be like the design reuse of components. I will just do some dirty coding here today, very quick and dirty coding of these calculations. For even our scene file, it doesn't have a well-defined format, as you can see. First, we'll have some format, but what I mean is that on Friday, when we announce the homework, you'll be able to start working on it right away, and you'll have 3 weeks on it. And we plan to finish ray tracing geometry today and start the shading part. And let me recap the overview of the ray tracing algorithm. The main components let me get this new page here. Our goal is to take a picture, take a photo of a virtual scene, right? So we have virtual scene, we have objects. So today we are going to actually see how our ray is going to interact with those objects. What does it mean to see those objects? And our primitive objects that compose a scene, that makes up a scene, will be triangles and spheres. So we'll have complicated objects represented as many triangles. And if we have this virtual scene, we need to have a camera to look at these objects. So that's what our eye is. We have an eye position, a camera set up in which the camera has some image window in front of it, and we have a discrete set of pixels that are on this image window. And what we do is we collect rays. Actually, the ray tracing is called backwards rendering because in real life, from light sources, light rays from light sources bounce off surfaces of objects, and then they come to our eye. But we are going to trace this backwards. We are going to start from the focal point of the eye and is going to ask this question: what is the so if we assume like a pinhole camera model that we have a very tiny hole, only light rays that are coming from a certain direction can come to this focal point and pass through the center of this pixel. Like a pinhole, it's very small, so there are 2 points, the focal point and the center of the pixel. So only a light ray that is coming off in a particular direction is going to come through this pixel. So the first part is we generate this ray. Then the second part will be, what does this, if you imagine you're looking through a very tiny hole through this pixel, in this direction. If imagine you're looking through a very tiny hole, this is what this pixel is seeing basically, and if you will be seeing only a small portion, a very small portion of your entire scene, and the next question we are going to be asking is, what is that we see? And the second part of the ray tracing algorithm, that also comprises the geometry part of the ray tracing algorithm, is to do ray object intersections. So in order to determine which object our ray that passed through this pixel sees, we are going to do ray object intersections or ray primitive intersections with our ray and against all of the objects in the scene. So that part is actually, we are going to implement the inefficient version of it, but there are ways to make your ray tracing faster by organizing your scene in a hierarchical manner. For example, there are binary space partitioning trees, there are quad trees, oak trees. If we just subdivide the scene into regions, it may be possible to know that certain objects that are, for example, on the left part of the scene, our array is impossible to intersect them. So if we can have data structures which help us prune out certain objects without having to do intersection tests with our array, it will speed up the process a lot. But in the original basic algorithm, which we expect you to code, if you're not going to, I think there's there may be a bonus part of the assignment in which high-speed ray tracers are going to receive a certain amount of bonus, but you can get a full grade, a grade of 100, without actually implementing this data structure. So that part is really not mandatory. We are going to ask you to implement the most basic version of ray tracing, in which in the most inefficient sense, we'll have our array and intersect it with all of the objects, because we don't know if we just have a list of objects, which, I mean, if you look at this picture from like a bird's eye view like this, you see that your array intersect with this sphere. It's obvious, right? But it's not obvious when you're coding it. If you have a bunch of spheres, a bunch of triangles, tens of thousands of them, when you have the ray equation, which triangle is going to intersect, or which sphere is going to intersect with your ray closest to the image plane, you may not know. Okay, so what we have to do is we have to have a for loop there for each object in the scene, intersect the ray with the object, and keep track of the closest intersection. That's also very important. When we are saying closest intersection, the intersection test is going to return a parameter t. For example, there may be this ray may intersect the sphere at this point at t is equal to, for example, 2.3. There may be another triangle behind the sphere. It may also intersect with this triangle at t is equal to, for example, 4. We are going to look at these parameters. So t is equal to 2.3. So this is a closer intersection than another intersection at t is equal to 4. There may be intersections, since our ray equation is going to be a line equations. There may be intersections that happen at t is equal to -2, for example. Our ray may intersect with an object that is behind us. So while we're keeping track of the minimum t when the ray is intersecting, we are not interested in intersections that are less than 0, because it means that they are going to be behind us. So there's a good question from Selim. So when there are transparent objects, how can we deal with that? Because if you're just keeping the closest intersection here, it obviously doesn't deal with transparent objects. So that's another, the most basic version of our ray tracing algorithm. We are going to assume that our scene does not contain any transparent objects. So, but how can you handle, if there are transparent objects, how can you handle them? So you need to, what does it mean to be transparent? For example, if I have a transparent blue marble, so it's bluish, there is some red opaque sphere behind it. So what we need to do is, we need to accumulate, we need to combine the colors of objects along the ray. So in order to deal with transparent objects, we need to rewrite our object intersection routine. Instead of keeping with the closest intersecting object, we need to maintain a list of intersecting objects. Maybe you may, if there's an opaque object that is intersecting the ray at that point, you may immediately prune out all the objects behind it. So you need to have a nice good data structure which helps you keep track of a list of objects such that in the list the object that is at the end of the list is always an opaque object, and the other objects that are in front of the list are objects that are transparent. So I think a data structure like a heap, a priority queue, I think will do nicely, but it also should allow you, for example, to do lots of deletions as soon as you insert something at some point. So it allows efficient insertion of objects. You need to obviously don't want to spend linear time every time you're inserting an object to your list. You have to have sublinear time, like log base 2n time, which inserting into a heap and removal from a heap takes this much time. So You need to basically keep this track of list of objects that are along the line. So this is how transparency can be handled. But in this course, we are not going to talk about transparent objects. Ozoja gives an advanced ray tracing course. I think in that course, he talks about transparency. Okay, so just the basic algorithm as in this introductory course. So if we don't have any transparent objects, you don't need to worry about those data structures and stuff. You only need to, in your for loop, all you need to do is maintain the minimum t, the minimum point of intersection, because our objects are not transparent. So the first object our ray hits, we are going to be seeing this object's color. Okay, now so that's basically the whole algorithm, but it's very simple, right? But why is it called ray tracing? I mean, we are shooting rays, obviously. We are tracing the ray backwards, but as soon as we hit an object, we just say the color of the pixel is this. Or do we? So why do you think this algorithm is called ray tracing? Any ideas? So is it over, for example, if this is a red sphere, for example, I say, okay, this is a red sphere, then this ray hits the object here. I'm going to just make this pixel color red. Okay, the entire pixel is going to be colored red, and that's it. And I'm going to, and we do this in the, we need to consider lighting conditions, whether the light ray hits this object, and what is the amount of photons that is bouncing off this point. If it's a surface directly under the light, we're basically going to consider the normal of the surface. At this point, still, we don't need to trace the ray itself, because the amount of light, the amount of photons that are bouncing off the surface, we are going to model it simply by using two vectors, which is the vector towards the light source and the normal vector of the surface. By using the dot product of these two vectors, we are going to, if, for example, there's a 90-degree angle between the light vector and the normal vector, it means that the photons are not bouncing, they're just grazing. That 90-degree means that it's not a small enough angle to bounce the light's rays. Still our ray hits here. Deepness, what do you mean deep? Can you clarify? We should trace here, trace them back to here, you may say, but it's still the same ray, right? I mean, it's the first object. Actually, there's some keyword, exactly, reflections. So that was the keyword I was looking for, close enough, reflective. So if a surface is reflective, like a mirror, for example, if this is like a mirror, or if it's a red reflective object, do we only see red here? No. Some blue triangle that is here, maybe, if I have a blue triangle here, part of the blue triangle may affect this reflective surface. And so this is why the algorithm is called ray tracing. They are reflective surfaces, exactly. For reflective surfaces, and if you want to see some bluish red here, blue being reflected off the surface of this red reflective sphere, so assume this is like a red reflective sphere, we need this is where we trace the rays. Okay, we are going to see details about this in the shading part, but the shading part basically comprises of three main functionalities. First of all, computing the diffuse color, computing the color that is reflected off the surface directly from the light source, light sources in the scene. Okay, and we are going to have a very simple illumination model for that purpose, and we are going to be tracing our rays. And here at this point, this ray, the color of this ray that is bouncing off the surface and that is reflecting the surface actually will be computed by using the same algorithm we did for this ray. So this part of the ray tracing algorithm will be recursive. We will treat as if, what if there's like a small pixel right here, and this is my ray that is passing through this pixel. What color is this pixel? Okay, so it's asking the same question, right? I mean, if we are interested in reflection from this surface, it's like we're asking exactly. So in this part, we're going to be doing something recursive. We are going to be asking the same thing from this triangle. What if this triangle is also a reflective object? Oh, keep bouncing your ray. But each time, since we rarely have 100% reflective objects in our scenes, which are mirrors. I mean, if you have a 100% reflective object, it's basically like a mirror with no color. Oh, the deepness, the 2D object from the 3D object, the deepness is going to be inherent the way we process this entire scene, okay? Because we are going to have perspective vision, and the 2D, 3D objects. Oh, maybe yeah. You mean deepness is going, and the deepness is going to come from shading. Actually, the light rays bouncing off different amount of the surface of the sphere in different places. So shading is going to give us that deepness feeling. Objects that are, some parts are brighter red, some parts are going to be darker red, and this is going to be just handled by, even we don't have reflective objects, we'll be able to just, without tracing the ray, by just taking into account this two vectors, the surface vector of the normal vector of the surface and the light ray, we can actually provide that deepness effect. That's we will probably be able to see today. Okay, but yeah, the ray tracing algorithm gets this name because of the recursive following of the ray in the scene. And usually we don't do this. I was just saying we don't have 100% mirror objects. The reflected ray actually contributes only a certain percentage to the surface. For example, you compute the blue color reflecting off this triangle, but while you're displaying that blue color, you don't display it pure blue because the reflection is just a little bit faded. So you just multiply that, whatever the reflectance coefficient of that reflectivity power of that surface is, you just multiply it with that. You just reduce the reflection amount. And as the ray, as we continue tracing the ray, this multiplication amount gets smaller and smaller. And in practice, we don't need to trace the ray more than 3 steps or 4 steps. So this recursive, if we do this recursion, we may actually stuck at infinite recursion, the ray bouncing off between 2 objects infinitely. I mean, it may be the case that for certain rays, the rays are just going to bounce off to the background, not hitting any other objects. That's where you may stop your tracing your ray. But if you keep tracing your ray as it bounces from objects, you may get stuck in an infinite loop as one ray bounces back and forth between a number of objects. So what we usually do in ray tracing is we limit this reflection depth, ray tracing recursion depth to 3 or 4, so that it's also not every one of these rays should we do intersection tests with the object, so it becomes less and less efficient at every recursion. And it's like another iteration of the entire pixel. So we usually limit it to some amount. So that's the shading part. As you can see in the geometry part, in the first part of the slide, the first thing we did last week was to generate this ray. Now we are going to see equations to intersect this ray with the sphere equation and with triangle equation. And after that, that the geometry part is over, the next thing is just computation of this color amount. What if this ray hits that object at this point? What is the color of this point? What do I see? We are going to take into account light surface interactions. We are going to take into account another, if the object is reflective. And this is very important. For non-reflective objects, you don't need to continue tracing your ray. Exactly, objects far away. You can also have, that's also a really interesting point. So when the objects are far away, the amount of light that reaches are, this is called light attenuation. Light actually, there are objects coming from, light coming from far away objects attenuates, it gets decreased, it diminishes. So we may also take that into account. It's actually, we are going to see how it can be implemented. Since we know this distance, we can have some kind of a quadratic model, in which we can, or linear model, in which we can decrease the amount of intensity illumination with respect to that distance parameter. So it's really easy to implement that part. It's called light attenuation. A very good question. Where do we keep that kind of reflectivity or transparency data of objects? Just like wherever you keep your scene objects. So we have this scene.txt, right? So here, what I had here was, I have some sphere information saying that I have a sphere centered at 333 with a radius of 4. That reflectivity or transparency information is not so much different than this information that I have for a sphere. It's just the data that you need to attach to your objects, okay? So the objects have geometry data, objects have color data. This is also called the reflectance of the surface, blue. The blue is like the color of the object is actually what component of the white light it reflects back. This is what color is. Or it may be a blue, but matte object, not reflective, okay? So the reflectivity data, whether it's a reflective object, whether it's a transparent object, everything can be stored together with some kind of an object class, object structure that you maintain. There is an object may have some complicated texture with it, okay? So this is where we keep those data. So we need to have a nice scene data format to be able to keep track of all these things. All right, so yeah, let me get physically based rendering. There is some physics involved here, but when people talk about physically based rendering, they usually refer to a more complex model than what we are going to have here. Ours is still physics-based, but we are going to have lots of abstractions. It's our model is going to be the simplest model. So when people refer to physically based rendering, they usually refer to more complicated physics equations embedded into these reflectivity and other stuff. Okay, so like for example, refraction patterns. We are not going to talk about refraction patterns, or for example, the fact that edges of objects actually appear blurry because the light rays are not exactly they're not exactly following straight paths. So actually, this is one of the first artists who observed this was Leonardo da Vinci. I mean, he was a great observer. I mean, if you haven't read his biography, I suggest you read the biography of Leonardo da Vinci by Walter Isaacson. So one of my favorite biography writers is Walter Isaacson, and he's also the author of that Steve Jobs biography. So I have read his Leonardo da Vinci's biography, and I mean, his biographies are not like biographies; they're basically like novels. So it's really fun to read them. And in that one, you just see that how observant Leonardo da Vinci is, and he devised this technique that, I mean, previously, artists were drawing objects with really sharp boundaries, but he observed the nature and his surroundings and figured out that when we look at an object close enough, even if we focus on that part, the edges of objects are actually not sharp. There are some blurriness. So, for example, probably the interaction of the light at the edges is really some complex quantum things may be happening at that point. I'm not also an expert in the area of photonics, but physics-based rendering usually refers to taking care of these advanced effects. And sometimes it also refers to, for example, fluid simulations, liquids. How do you model liquids? How do you model interactions of objects? For example, two objects crashing, objects that fall apart. So physically based rendering usually also refers to that detailed physical modeling of objects. Okay, so this is basically the entire ray tracing algorithm that we're going to learn. We're going to learn how we can do this shading part, how we can provide that depth to objects, how we can deal with reflective objects, reflective surfaces, and there's one final thing in shading, which is shadows. Okay, how do we generate shadows? What does it mean to be a surface objects to be in shadow? For example, if this triangle, this point on the triangle, is it in shadow or not? If some object will be in shadow if there is a light source in the scene and if the light rays do not reach that point of the surface, the object will be in that part of the surface will be in shadow. So we are also going to keep track of this, but not by recursively tracing our ray, but by looking at the surface point, by looking at this vector from the surface point to the point light source. If this ray from the surface point to the light source is intersecting another object in between, it means that this light ray cannot reach this point. Therefore, this part should be in shadow. So as you can see, lots of ray object intersections. We do ray object intersection to determine the color, to determine the reflectance, to determine whether there's shadow or not. So the geometry part we're going to be seeing today is going to be taking care of all these things, okay? And when something is in shadow, should we have a complete black color for that shadowy part? Actually, in real life, what happens is that even if we have light sources in the environment, in real life, the photons bounce everywhere. So we are going to have a basic illumination model, which is going to compose a surface color, is going to be composed of three components: the diffuse component, the specular component, and the ambient component. So diffuse component is going to try to model the light rays that bounce off in every direction from this surface, and one of these light rays is the one that is coming to our pixel. That's what is called diffuse. The light ray, even coming from here, the light ray from a point light source is coming to the surface, but it's bouncing off in every direction. Why does this happen? I mean, we know that in physics. If this is a surface, if this is a light source here, it's coming to this surface like this, it's going to bounce in one direction, right? The angle of incidence is equal to angle of reflection. We all learned that in physics. So how come a light source, a light ray coming from a light source from this angle, I'm saying that the diffuse model models reflections in every direction from this surface, okay? The reason is that in real life, no object is as smooth as this perfect surface. In real life, if we look to, for example, a cloth, okay, or some wood, when the light rays hit the surface of the wood, a wood, for example, it's not bouncing off in just one direction. This only happens if this is like a mirror-like perfect smooth surface. If it's wood, if you look at wood with a microscope, you're going to see that its surface is going to be all this. It's not smooth at all. It's all jagged and lots of tiny bumps and holes everywhere. So when light ray comes here from this microscopic small non-smooth surface, reflections are going to occur in every direction. So that's what diffuse component is going to try to model. Okay, our simple model is not going to actually take care of all these individual bumps and ridges on the surface of the moon, but it will be a simple abstraction of that fact. Okay, we'll just basically, we observe something and we'll just develop a very simple mathematical model. That's the diffuse component. The specular component is going to try to model this specular reflection from shiny surfaces. Okay, it will have this component, the light ray that is bouncing off in a particular direction, and the shininess of objects or mattness of objects are going to be dealt with by combining these components by different coefficients. We're going to see that. And the last component is the ambient component. This ambient component is actually independent of the light source. It tries to model the fact that in real life, we don't have only light rays coming off from the light source. In real life, the light rays bounce off every object in the environment. So there is some ambient default light in the environment. Even if you're in completely total shadow, you're not completely dark. Okay, so this is what the ambient component is. And when the object is in shadow, we're just going to use this ambient component. And all these things, we're going to talk about the details of these things in the following 2 weeks. Okay, so I just summarized the entire ray tracing algorithm with the geometry and shading part. But that's it. If we do that, and if we code that, you'll see that we'll magically see nice spheres and triangles in RC. So let's go ahead and start coding, okay? Yes,
Hocam,
sure.
like in real life, all the things that we see are actually the reflections of the light,
Exactly,
right?
exactly. So
Like
if
even
there's
if
no light,
it's
exactly,
math or not.
exactly. So when there's no light, it's totally black. So light sources are therefore really important. Exactly. In real life, everything we see are light rays bouncing off objects, even if it's doesn't see the entire. So, for example, when you look at the underneath of your table, you still see it's not completely dark because light rays are bouncing off everywhere. So, the ray tracing algorithm is a very simple algorithm that tries to model the interaction of the light with the objects. There are actually more realistic algorithms which generate pictures, which looks very much like the real life. For example, one such method is called radiosity. Okay, so this is another algorithm which just like integrates all these things that are light rays bouncing off different parts of the scene in an integrative manner in iterations. And it's very time consuming, but when it generates photos, the graphics that it generates, it looks very much like what we see in real life. So the whole goal in computer graphics is to devise these algorithms that try to model the interaction of these things. But there are lots of things at hand here. For example, we want to be as efficient as possible. Why is ray tracing, for example, hasn't been used? Ray tracing is now being used in real-time graphics applications in the recent years, thanks to the graphics processing units. But ray tracing, I didn't play games done with ray tracing when I was 20 years old, 30 years old. All the games I played, in the second part of the course, we are going to see a different algorithm which is implemented in OpenGL, the forward rendering algorithm. It's going to generate, for example, reflections in that forward rendering algorithm is very difficult to get reflections. You need to write some additional code. By default, it will just generate this dull looking pictures, but with some tricks, we'll be able to have some nice, we are going to try to get them nicer. But this other algorithm, which is much more efficient than ray tracing, is preferred because of its computational efficiency. As I said, there are two things at hand. Yeah, right. These days we cannot. You'll play soon, okay? So you are going to be playing. You're not going to say we cannot play ray tracing, real-time ray tracing games. You will be playing real-time ray tracing games soon enough. So the hardware developments are amazing, and now some graphics cards, yeah, they are too expensive, but yeah, they will get cheaper. The capabilities of the graphics cards we have these days, 20 years ago, they were like $1 million graphics workstations. Now you can get $100 graphics card. That's better than that $1 million graphics workstation 20 years ago. So the developments in GPU are going to get better and better. So you'll be able to play ray tracing games. But still, the main reason I talked about this was there's also computational efficiency. I mean, we have these simplistic models. So why do we model the entire, so light rays are bouncing everywhere, we have this complicated physics going on, but the basic illumination model, diffuse, specular, ambient, it's so simple to compute, and you're going to see. So let's go ahead and start coding right away. Okay, now let's see. I want to see our spheres today. Now, the first thing is, I wrote our scene in really free format, free text format in this file, but let's make it some kind of a format. The first thing, for example, that we need from this is the resolution. That's what I'm going to have in the first line. So we need to decide on some kind of a file format for our scene. We can have the camera definition and the scene definition in two separate files if you want. In the homework, we are going to be provided with a nice structured scene and camera format in XML, and we will provide a simple XML parsing library for that. So we'll try to make it as easy as possible for you. Now, so this is our resolution. We have so the distance to the eye. So let's have the 2 units, left boundary, right boundary, bottom boundary, and top boundary. So the first 7 numbers are about the image window I have here. Okay, then also let me put my camera information here. 5015, I have a camera located at that point. I'm looking at, this is my gaze and my up vector. So as you can see, if you just have this file format like this, you have to be very careful about what these numbers mean, because I just deleted lots of things here. You need to know what these are. Okay, so 3, 3, 3 is your sphere, and radius of 4, and blue. So how do we indicate blue color here? Let's have some numbers for that too. Let's, for example, have the blue color as an RGB kind of way, like 001. Okay, they may be your reflectance, or 00255. We can say the color of the object will be directly given here as a color, but what we are going to have as the color object is, the color of the object will be modeled as what percentage of light and that comes to on its surface, it reflects back. So it will be better to have these numbers between 0 and 1 to indicate some kind of a ratio percentage. For example, if it says 0.5, this will mean that if I have a white light source, the surface of this sphere, it reflects 0% of the white light source, its red component. It's reflect no red component. It doesn't reflect any green component. It reflects 50% of the blue component that comes to it. For example, if in my scene I have a red light source, it means that the surface of this blue object will appear black. Okay, so if, for example, if you're wearing some blue jacket, and if you go to some place where the entire lighting is just red, your blue jacket is going to appear black. So the idea is the same here. Okay, so this again, these numbers for some sphere, I mean, if you don't know what they mean, I mean, we need to really know what this format means so that we can parse it correctly. And so let's have a red sphere, a bright red sphere, which reflects all of the red light source. So the entire scene right now can be easily parsed here, and we need to also have a light source. That's what's missing here. We don't have a light right now, but that will become, we will use that light in the shading computation I mean, in the next week or on Thursday, we talk about that. But let's go ahead and write our first piece of code. What we are going to be doing. First, generate an image of this size, and we need to write a function to generate our array. So what I'm going to be doing is I'm going to just write a very simple C code here. Okay. Can I zoom in on this, or maybe I can do it in Notepad+. So any C compiler, C++ compiler, you may use whatever you're familiar with. Let me write it here again in Notepad++, which is nicely larger fonts here. So let's get a new file. So I'm going to write, as I said, dirty coding, a pure C here. So I'm going to have an image file, which I'm going to have here. Oh, by the way, let's have some, since we're going to be working with lots of vectors, okay, so I'm going to have a float vector, float x, y, z. Let's call this one vec3. Okay, so I can have, for example, my ray may be a vec3 object. Okay, whatever I have here. That's not an object, it's a simple struct, as you can see here. A simple struct of xyz, which contains xyz values, will be a three-dimensional vector. For this purpose, actually, you don't need to define your own data structures and vector library. There's a library called GLM. Let's see. OpenGL Mathematics, GLM library. So yeah, it's in GLSL, optional mathematics here. So it's just say OpenGL. So this is just a header file, actually, GLM. OpenGL Mathematics is a header-only C++ mathematics library for graphic software based on the OpenGL shading language specification. So it's very, so there is a vector 3 there, vector 4, matrices, so it's really easy to work with vectors if you're using GLM. But the things that we're going to be doing here are going to be very simple. So let's stick on to this simple thing first. Now, what is my image? My image will be basically an integer array, okay, an integer matrix. So I can actually have declare my image to be an integer matrix like this. First, let's scan my resolution. So I have there are integers nx and ny, nx and y. So let's first read those, okay. My resolution I read first, and just allocate an image with some initialize with some background color. And I need to have a file that's going to write this onto a ppm file, right? So my image is going to be, so as you can use C++ and use new and do these things much easier than that, but yeah, I'm just coding it in old school way. So the first, I'm going to have nx rows, and each row is going to have nx and y values. Nx, and I'm going to also, now let's have my I and j's here. For I is 0, I less than nx. So let's allocate each row to and each column. So each column contains ny. So I have this many rows and I have this many columns. So just I allocated myself basically an image of image ij. So let's initialize that. For I is equal to 0, I is equal to nx, I plus plus. Do the same thing for j. So, and I'm going to initialize my background. Oh, by the way, my image, is it just a single integer? I mean, this will be true if you're only interested in grayscale images, right? Actually, every cell in the image has to be vec3, and in that case, it's like a float, maybe vec3i. Let's maybe we need to have different type of vectors. One, an integer vector which is composed of integers x, y, z, and this x, y, z may mean RGB in our case. Okay, so it's going to be actually every pixel of my image is nothing but 3 integers. It's not just a single integer. That was one mistake I did. So here, by the way, this should be size of int pointer. Okay, I need to have this many int pointers, and I need to have this many ints. Okay, and this is going to be actually vec3 pointer. All these are vec3. And each column is going to have this many vec3s in it.
vec3i.
Yeah, exactly. Thank you. Yeah. Thank you for the correction. So I have an integer vector. That's my image. Okay, now I can actually initialize it. J is less than ny, j plus plus, and so actually I can write a single line here. Sorry about this. So image ij x is equal to image ij y and image ij z. And what do we want our background color to be? Black. You just put 0 here. If you want white background color, put 255 there. Okay, so now let's have a black background image. Okay, so this means that the RGB values of my image initially, so I set it to the background color of 0, black. So if we actually have a specific background to be specified in the scene file, we can have that input here. Okay, now this code just creates a black image, but we still don't have that black image. So we need to have our final line here should be to get this image and write it to a file. Okay, we can have a function for that, right? ppm, which gets an image. Actually, we already have that as a global variable. But it doesn't matter. We can also parameterize later, maybe. I'm not sure. So what we need to do is, in order to write the ppm, first I need to also have std lib for other stuff too. Maybe std lib.h. Let me not forget that. So let's open a file. Output, let's call it output, our ppm file. Okay, now how does the ppm, what does the ppm format look like? Let's go ahead and take a look at that. I forget how so it started with p3 something, so let's take a look at that. It was in I think in images and cameras here. Let's take a look at our ppm file. Yeah, this one. I think this is optional, this simple ppm, or maybe it's the name, or yeah, let's actually do that. P3 and fprintf fp. All right, and I'm going to write that output.ppm here. I don't know, maybe it may be a required comment in some cases. Then it's resolution and it's color information. So I'm going to write nx and ny. So maybe we can pass this nx and ny also as parameters to this function. So the next thing is going to be writing NX and NY, NX and NY here, and writing that 255 part. We are going to be writing colors. Our colors will be between 0 and 255, and then I will have the same loop here, and I will just basically write my image color values here. So let's see whether we can get our first ppm image, and then I'm going to write the generate rate function, and then let's see what we are missing size of F'21. Where am I missing? On line 40. Size of, oh yeah, thank you. So thank you for that correction. Now what I'm going to do is here I'm going to write each in a different line. So it's going to be something like this: fprintf, just the end of line after every row I'm going to put in my file. So, and write the colors in a row here. So, oh, by the way, now, actually, right now, I just confused what NX and NY was, right? Because I just treated this image as if NX is the number of rows. NX was actually the number of colors, right? If you have 2000 by 1000 image, NY is the number of rows. So while we're this mistake easily correctable, but you have to also make sure that you know this thing, the difference between the way we treat matrices and the way what this NX and NY means. So actually the role of NY actually is the number of rows here. So their role is switched. So when you read, for example, I mean, if you're consistent, you may resolve this in any way you like. But since NY is the dimension, it's the height of the image, and if you treat your image as a matrix in which the first index indicates the number of rows in your image, it should correspond to Y, all right? So you need to make this switch here, and similarly the same here, NY, NX. Okay, so the difference, let me repeat that. NY, which is the height of the image, that height of the image is given in NY when we have a 2000 by 1000 image. 2000 by 1000 image is not a 2000 by 1000 matrix in terms of matrix terms. It has 1000 rows, right? I mean, in matrices we write the rows first. That's why there's this discrepancy between matrices and images, but you can easily resolve this situation. And you can resolve it in different ways. This is not the only way to resolve this situation. Just if be consistent in what you're doing, it shouldn't be a problem. But in this case, I'm just going to be switching NY and NX their roles like this. Okay, now I'm going to be printing three things separated by space, and then maybe a tab later, or maybe another space like this. So I'm going to be writing, do we have a tab between these things? Yeah, maybe a tab at the end. I mean, in a white space probably will do. Now, image I, j, dot x, y, z. So I'm going to be writing these values. Right now it's a very boring program, which is just going to be writing 255 or 000 into a file, and that's it. Okay, so but let's try this, and after that we're going to have a break. Okay. Oh, by the way, this is going to be a C file. Let's put it in the same directory as this one, as C source file. Oops, not this one. The one just above that. yeah, let's call it my ray tracer, raytracer.c. Okay, so and you can compile it in many different places. I'm going to be using WSL, Ubuntu on Windows. I have a Windows here. I'm using Windows subsystem on Linux. You can also use any. There's MinGW that you can have on Windows as your GNU C compiler. But I will be using this one. Was it CENG? Yeah, 477. Now, what was the name of the file? Ray tracer. So we'll have obviously many errors. So our write ppm is should also have this nx and ny. That's one error that I know. I can see there are too many arguments. Oh, okay. So we will be reading from a file. Actually, we're not reading this from a file. My format strings are all wrong. Now I got them correctly. Do I have any other error here? All right. Makes a pointer from integer directly. Yes. Vec3. Oh, Vec3 was our Vec3s were pointers, right? It shouldn't be pointers. Let's see. Vec3i. No, it should be okay. Oh, we missed that. Oh, okay. Oh, yeah, we missed an FP at some place while we were on line 31. Thanks a lot for that. Oh, yeah, the file pointer. We're reading this. We're writing this to a file. Thank you so much for that. Yeah, and that's it. Now, so when we run this, I'm going to run it since we're by giving our input scene1.txt, something like that. So it's waiting that 2000 by 1000 thing here. Okay, so and it wrote that. That's the only thing that we read. We just read the resolution and write some ppm file out. So we have a scene file here, right? Yes, scene.txt. All right. So yeah, we have an output ppm. So let's take a look at how this output ppm looks like. Yeah, P3 output ppm 2000 by 1000, 255. Yeah, we were able to write a completely black image. And can we see it? So the real ray tracing will start like this, but hopefully it's going to get better. So ppm seems that GIMP is able to visualize ppm files. That black image takes 11 megabytes space here. There's one thing, there's image magic that you can use to convert these ppm files to. So yeah, this is what we did. So this is our 2000 by 1000 image. It's completely black. A high resolution black image. And hopefully we'll be able to see our spheres after the break. So let's have our break. We're going to generate our rays and intersect them with our spheres. Okay, we haven't seen the intersection equation yet, but it's going to be not very difficult. Okay, now yeah, let's have a 10-minute break until 10:50, and we are going to continue with that after the break.